Something changed on October 30th, 2025, at precisely 1447 Universal Coordinated Time. In that moment, at the Allen Telescope Array in Northern California, something happened that scientists had been simultaneously hoping for and dreading for over 60 years. A signal. Not from the depths of space, not from some distant star system light years away, but from right here, inside our own solar system. From an object we'd been watching, tracking, analyzing for months, an object we thought we understood. The interstellar visitor known as 3I Atlas had just done something that comets aren't supposed to do. It transmitted a radio signal, and what that signal contained is making some researchers ask questions that, until very recently, would have gotten them laughed out of their departments. Let me tell you what happened in those crucial moments, because what unfolded over the next 11 minutes and 34 seconds has changed everything we thought we knew about this visitor. And the more scientists analyze the data, the more uncomfortable the implications become. Dr. Sofia Ramirez was 3 hours into her shift at the Berkeley SETI Research Center when the alert triggered. She'd been monitoring the Allen Telescope Array's automated scanning protocols, a routine task she'd performed hundreds of times over her 12-year career. The array, a collection of 42 radio dishes spread across the Hat Creek Valley, had been doing what it always did: listening. Searching, looking for patterns in the cosmic static that just might indicate someone out there was trying to make contact. The system had flagged thousands of signals over the years: satellites, aircraft, terrestrial interference, even a microwave oven in the facility kitchen once triggered an alert that took weeks to track down. So when the console lit up with a detection alert, Ramirez's first instinct was to dismiss it. Another false positive, another piece of human-generated noise masquerading as something interesting. But then she looked at the frequency. 1.42040.751 gigahertz, the hydrogen line, the exact frequency that every SETI researcher knows by heart, the frequency they've been monitoring since Frank Drake first pointed a radio telescope at the stars in 1960, the frequency that, in theory, any technological civilization would recognize as special, as significant, as the universal calling card of intelligent life. Ramirez felt her pulse quicken. She ran the automated verification protocols, checked for satellite interference, verified the array's orientation, confirmed the timestamp. The signal was real. It was stable. And it was coming from inside the solar system. She triangulated the source. Not from Earth, not from any known satellite, not from Mars, not from Jupiter's moons, not from any of the usual suspects. The coordinates placed it at approximately 0.3 astronomical units from Earth. She pulled up the ephemeris data, the catalog of known objects in that region of space. There was only one object there: 3I Atlas, the comet from beyond the stars that had been approaching perihelion, its closest point to the sun. The object that, just hours earlier, had been the subject of routine observational reports noting its unusual brightening behavior. That object was now transmitting a radio signal. Ramirez reached for the phone to call her supervisor, then stopped. She needed confirmation first. Independent verification. Because if she was wrong about this, if this turned out to be some equipment malfunction or elaborate interference pattern, she'd never live it down. She routed the signal data to the Green Bank Telescope in West Virginia, the largest fully steerable radio telescope in the world. If the signal was real, Green Bank would see it too. She sent the coordinates, the frequency, the timestamp. Then she waited. 4 minutes felt like 4 hours. When Dr. Chen Wei's response came through from Green Bank, it was 3 words long: "We confirm detection." That's when everything accelerated. That's when the carefully structured protocols of scientific verification collided with the reality that something genuinely extraordinary was happening in real time. Within minutes, other facilities were being contacted. The Very Large Array in New Mexico, the Parkes Observatory in Australia, China's FAST telescope. Every major radio astronomy facility that could physically point at that region of the sky was being asked to verify, to confirm, to witness what was happening. And one by one they did. The signal was real. It was narrow band, impossibly narrow for any natural phenomenon. It was stable, locked onto that hydrogen line frequency with a precision that made no sense for plasma interactions or magnetic field fluctuations. And it was pulsing, not continuously transmitting, but pulsing in a regular pattern, on for half a second, off for 0.3 seconds, on, off, off. Mathematical precision in a cosmos that favored chaos. But here's what made those first few hours so chaotic, so unprecedented. NASA said nothing. For 6 hours after the initial detection, while amateur radio astronomers around the world were picking up anomalous signals and posting about them on forums, while SETI researchers were frantically coordinating observations and running analyses, the official channels were silent. No press release, no statement, no acknowledgement that anything unusual was happening. It wasn't until 2052 UTC, more than 6 hours after the signal began, that NASA's Near-Earth Object Coordination Center released a statement, and even then it was carefully worded, almost painfully vague. Investigating anomalous radio source detected in inner solar system. Further analysis ongoing. No mention of 3I Atlas specifically, no mention of the hydrogen line frequency. No mention of the pulsing pattern that was becoming increasingly obvious to everyone who was watching. The statement could have been describing a glitch in a satellite, a solar flare, anything. It told the public almost nothing. And that silence, that deliberate vagueness, is what made people start asking questions that went beyond the science. What did NASA know that they weren't saying? What had they seen in those first 6 hours that made them so cautious about disclosure? Because by then, SETI's Breakthrough Listen project had made a decision that would prove crucial. They released the raw data. All of it. Unfiltered, unprocessed, available for download to anyone with an internet connection. Within hours, thousands of researchers, amateur and professional, were analyzing the signal. And what they found was impossible to ignore. Let me tell you about the signal itself, because this is where the story moves from unusual to genuinely unsettling. The frequency, as I mentioned, was 1.420405751 gigahertz, precise to 9 decimal places. This is the natural emission line of neutral hydrogen, the most abundant element in the universe. It's produced when the electron in a hydrogen atom flips its spin state, releasing a photon with a very specific wavelength, a wavelength that corresponds to that frequency. Radio astronomers have known about this line since 1951. SETI researchers have been monitoring it since the very beginning of the search for extraterrestrial intelligence, because any civilization that understands radio astronomy would recognize this frequency. It's a universal constant, as fundamental as the speed of light. Using it to transmit isn't just coincidental, it's deliberate. It's saying, I know you're listening here, I know you understand what this frequency means. But natural sources produce this frequency too. Clouds of hydrogen gas in interstellar space emit at this wavelength. So frequency alone isn't enough to conclude anything. What matters is the bandwidth, how spread out the signal is across the spectrum. Natural sources, even when they emit at the hydrogen line, spread their energy across a range of frequencies. Turbulence in the gas, temperature variations, magnetic fields, all of these factors broaden the signal. A typical natural hydrogen line emission might have a bandwidth of thousands or millions of hertz. This signal, 0.3 hertz. 0.3. That's not just narrow. That's impossibly narrow for anything natural. To maintain that kind of frequency stability requires technological precision. It requires a transmitter that's controlled, regulated, intentionally focused. Nature doesn't do that. Nature doesn't produce pure tones. The signal strength was another factor that demanded attention. Measured at Earth, it registered at negative 284 decibels relative to 1 milliwatt. Incredibly weak, barely distinguishable from background noise, which is why it took SETI's sensitive equipment to detect it. But when you account for distance, when you work backward using the inverse square law to calculate how strong the signal must have been at its source, the 0.3 astronomical. Units away, the numbers tell you something important. This wasn't some massive broadcast beam. This was a relatively modest transmission, perhaps comparable to the power output of a small terrestrial radio station. Just strong enough to be detectable if someone was listening at the right frequency. Just strong enough and no stronger. Like it was calibrated. Like someone or something knew exactly how much power was needed to reach the inner solar system. Then there was the polarization. Radio waves can be polarized, meaning the electric field oscillates in a particular orientation. Natural sources typically produce unpolarized or randomly polarized emissions. This signal showed right-hand circular polarization. Consistent, stable, throughout the entire transmission. That's another technological signature, another indication that this wasn't plasma turbulence or magnetic reconnection or any of the usual suspects that produce radio waves in space. This was structured, controlled, designed, and the Doppler shift confirmed what everyone already suspected. The signal was moving. Not stationary in space, but traveling at exactly the velocity of 3I Atlas relative to Earth. You could calculate the object's speed from the Doppler shift alone, and it matched perfectly with the orbital data that had been tracking the comet for months. The source of this transmission was physically located at, or on, or within the interstellar visitor. There was no ambiguity about that. Whatever was transmitting, it was doing so from that specific object as it made its closest approach to our sun. The signal lasted 11 minutes and 34 seconds. Not a round number in any time system humans use. Not 10 minutes, not 15. 11 minutes and 34 seconds, and then it stopped. Complete silence. As abruptly as it had begun, it ended. 3I Atlas continued on its trajectory, continued sublimating water vapor and carbon dioxide as comets, continued behaving in every other observable way like a chunk of ancient ice and rock that had wandered in from interstellar space. Except for those 11 minutes and 34 seconds when it spoke, when it transmitted a signal on the frequency that every radio astronomer in the world associates with the search for intelligent life. At the exact moment of its closest approach to the sun, the timing was precise, the frequency was precise, the polarization was, and within that transmission, encoded in the amplitude of those pulses, in the pattern of on and off, was something that would take days to fully recognize, but once seen, could not be Someone ran the pulse pattern through a basic analysis algorithm, looking for any kind of structure. And there it was. Simple, elegant, unmistakable. The first 15 pulses, when you counted them, when you separated them from the gaps, formed a sequence. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47. Prime numbers, the building blocks of mathematics. Numbers divisible only by themselves in 1. Numbers that any mathematical civilization would recognize, would understand, would know are not produced by random natural processes. This wasn't a greeting, this was a proof. Proof that whatever sent this signal understood mathematics, understood number theory, understood that the recipient would recognize the significance of primes. It was the cosmic equivalent of saying, I am intelligent, I understand logic, I am capable of abstract thought. Now you know I exist. Dr. Chen Wei didn't sleep for 3 days after the detection. He couldn't. Every time he closed his eyes, he saw those prime numbers scrolling across his mental vision, pulsing in that perfect rhythm. 2, 3, 5, 7, 11. The most fundamental sequence in mathematics, transmitted from an object that had traveled through the darkness between stars for billions of years. On the 4th day, fueled by coffee and the kind of manic energy that comes from knowing you're working on something that will be in history books, he made the discovery that changed everything. The prime numbers weren't the message, they were the key. The signal wasn't just on-off pulses of equal strength. When you looked at the amplitude, the power level of each pulse, it varied, subtly but consistently. Chen had been so focused on the timing of the pulses on the prime number sequence that he'd initially dismissed the amplitude variations as noise, as natural fluctuations in the signal strength. But they weren't random, they were structured. He ran the amplitude data through a Fourier analysis, looking for periodic patterns, then through a wavelet transform, then through a dozen other mathematical techniques designed to extract signal from noise. And there, buried in what everyone had assumed was just the carrier wave, was another layer of information. Mathematical constants. Not just any numbers, but the specific values that appear over and over in advanced mathematics and physics. Pi, the ratio of a circle's circumference to its diameter, encoded to 15 decimal places. 3.145923893. And 93. Euler's number, the base of natural logarithms, fundamental to calculus and complex analysis, encoded to 12 decimal places, 2.79288845. The golden ratio, phi, that strange number that appears in everything from nautilus shells to galaxy spirals to the proportions of the human body, encoded to 10 decimal places, 1.618889887. These weren't arbitrary choices. These were the numbers that any civilization studying mathematics would eventually discover. These were universal, transcending culture or biology or the specific conditions of any homeworld. These were the numbers that said, we don't just understand arithmetic. We understand advanced mathematics. We've discovered calculus. We know about irrational numbers and transcendental constants. We're not just intelligent, we're sophisticated. The implications rippled through the scientific community like a shockwave. If the prime numbers were the greeting, the mathematical constants were credentials. They were a way of establishing intellectual credibility, of showing that whoever designed this signal had reached a level of mathematical understanding comparable to or exceeding humanity's own. But why include them? Why not just send the primes and be done with it? Dr. Claudia Reeves at MIT spent 72 hours analyzing this question, and her conclusion was elegant in its simplicity. They're establishing a common language, she told the emergency symposium that had been hastily organized at the International Astronomical Union. First, they prove they're intelligent with the primes. Then they prove they're mathematically advanced with the constants. They're showing us they think the way we think, that we can communicate using mathematics as a foundation. They're building trust. They're saying, you can decode what I'm sending because we share the same logical framework. But there was more. Dr. Wei, now working with an international team that had grown to include researchers from 17 countries, kept digging. The frequency modulation, the subtle shifts in the signal's exact frequency within that impossibly narrow 0.3 Hz bandwidth, contained yet another layer. This one took longer to decode because it required understanding that the variations weren't random drift but intentional encoding. What they found was a coordinate system. Not human coordinates, not right ascension and declination as measured from Earth, but galactic coordinates, a way of describing location that would make sense to anyone anywhere in the galaxy. And encoded in those coordinates was a direction, a specific point in space. When they plotted it, when they converted those galactic coordinates into something their star charts could interpret, it pointed to a star. HD 939X2, a G-type main sequence star in the constellation Carina, 178.3 light-years from Earth, a star that had been cataloged, observed, analyzed, a star that had, in 2021, been confirmed to host at least one exoplanet, HD 93962b, a super-Earth orbiting in what astronomers cautiously called the habitable zone, the region around a star where liquid water could exist on a planet's surface. The signal was pointing home. It was saying, this is where I came from. This is my origin. If you want to know more, look there. The discovery sent telescopes pivoting. Every facility that could observe HD 93962 suddenly had had requests flooding in, and what astronomers found when they looked more closely at that system made the signal's message even more profound. The star was old, 5.8 billion years compared to our sun's 4.6 billion. It had been burning steadily, producing heat and light for longer than our entire solar system had existed. If life had emerged there, it had had more time to evolve, more time to develop, more time to reach for the stars than life on Earth. The planet, HD 93962b, was larger than Earth, but not so large that it would be a gas giant. Its orbital period was 487 days, placing it firmly in the zone where temperatures could support liquid water. Its mass suggested it could retain an atmosphere. Everything about that system whispered possibility. And now an object claiming to have originated there was passing through our solar system, transmitting mathematical proofs of intelligence and pointing back to its birthplace. But the analysis wasn't finished. Machine learning algorithms, artificial intelligence systems trained on signal processing and pattern recognition, were turned loose on the data, and they found something the human researchers had missed. A fourth layer, even more subtle than the others. Embedded in the precise timing of the pulses, in microsecond-level variations that human perception couldn't detect, was trajectory data. Not just I came from HD 93962, but here's the path I took to get here. Three-dimensional coordinates describing motion through space, velocity vectors, gravitational influences. When the AI reconstructed the trajectory and ran it backward through time, accounting for galactic rotation, stellar motion, all the complex dynamics of objects moving through the Milky Way, it traced a path that led back approximately 7 billion years ago, give or take several hundred million years, to the HD 93962 system. 7 billion years. The number hung in the air like a weight. This object, if the trajectory calculation was correct, if the embedded data was accurate, had been traveling through interstellar space since a time when Earth was barely 2 billion years old. Since a time when the most complex life on our planet was single-celled organisms floating in primordial oceans. It had been launched or had departed or had been sent from HD 93962 when that star system was less than 1 billion years old. It had been traveling through the galaxy for longer than complex life had existed on Earth, and it had survived, somehow through all those billions of years of cosmic ray bombardment, through encounters with interstellar gas clouds, through the gravitational perturbations of passing stars and the radiation of galactic cosmic rays, it had remained intact. Functional. Capable of detecting a star, approaching it, and transmitting a signal. The scientific community was fracturing. You could see it in the published papers, in the conference calls, in the heated debates that were now happening in public as well as behind closed doors. On one side were the researchers who insisted that there must be a natural explanation. Yes, the signal was unusual. Yes, the encoding was sophisticated. But nature is vast and strange and capable of producing phenomena we don't yet understand. Perhaps there was some exotic plasma physics occurring in the comet's coma, some interaction between the sublimating gases and the solar wind and the object's magnetic field that could produce coherent radio emission. Perhaps the mathematical patterns were coincidental, the result of humans finding patterns where none truly existed, seeing meaning in randomness because we're desperate to find it. Dr. Helena Vasquez at Harvard became the leading voice of this perspective, arguing forcefully that extraordinary claims required extraordinary evidence, and that a single 11-minute transmission, however intriguing, was not sufficient to overturn the default assumption that 3I Atlas was a natural object. But the counter-arguments were growing stronger. Dr. Kenji Tanaka in Tokyo published an analysis that became widely cited. Show me the natural process that generates prime number sequences. Show me the astrophysical phenomenon that encodes mathematical constants to 15 decimal places. Show me the plasma instability that points to its star of origin using galactic coordinates. His point was simple and devastating. Each individual anomaly might, with significant effort and generous assumptions, be explained naturally. But the combination, the layering of multiple sophisticated encoding schemes, the timing of the transmission at perihelion, the use of the hydrogen line frequency, all of it together required so many unlikely coincidences that the natural explanation became more extraordinary than the artificial one. And then there was Avi Loeb, the Harvard professor who had become simultaneously famous and controversial for his willingness to discuss artificial origins for Oumuamua, the first confirmed interstellar visitor. Loeb had been ridiculed by many of his colleagues for suggesting that Oumuamua's unusual acceleration, its elongated shape, its lack of outgassing could be consistent with a light sail, a thin reflective sheet pushed by starlight. Most astronomers had dismissed his hypothesis as sensationalism, as attention-seeking. They'd argued for natural explanations, insisting that Oumuamua was just a comet whose ice was sublimating in a way we hadn't observed before. But then the more data they collected, the harder the natural explanations became to maintain. The object's acceleration didn't match models of comet outgassing. Its shape was unlike any solar system object, and it had come from interstellar space on a trajectory that suggested it hadn't been gravitationally bound to any star for potentially billions of years. Now with 3I Atlas, Loeb was speaking out again, and this time his message was more pointed, more urgent. We dismissed Oumuamua because the hypothesis made us uncomfortable, he wrote in an op-ed that appeared in the New York Times. We chose the explanation that fit our preconceptions rather than the explanation that fit the data, and now we're seeing the same pattern repeat. An interstellar object does something unexpected. It transmits a signal on the frequency we've been monitoring for 60 years, encoded with mathematical proofs of intelligence, and we're looking for ways to explain it as natural, because the alternative challenges are worldview. But when did science become about protecting our worldview? When did we decide that some hypotheses are too uncomfortable to investigate seriously? He was calling for transparency, complete data release, international cooperation, and most controversially, he was calling on NASA to release everything. Not just the radio telemetry, but the spectroscopic analysis, the infrared observations, any classified briefings that had been prepared for government officials. His argument was straightforward. This wasn't a matter of national security, this was a matter of scientific inquiry, and science worked best when data was shared, when multiple independent groups could analyze the evidence and test competing hypotheses. The signal from 3i Atlas wasn't a military threat. It wasn't a weapon. It was potentially the most important data humanity had ever collected, and it needed to be studied by the full resources of the global scientific community, not gatekept by any single institution or government. But NASA's response remained cautious. Their updated statement, released 8 days after the initial detection, acknowledged the signal but committed to nothing. Analysis of radio emission from Object 3i Atlas continues. Multiple hypotheses regarding the source and nature of the emission are under investigation. No conclusive determination has been reached regarding natural versus artificial origin. Further observation and analysis required. The statement satisfied no one. It was too vague for the public, too non-committal for the scientific community, too defensive for the advocates of transparency, and it raised an obvious question. If the analysis was truly ongoing, if no conclusions had been reached, why not release the data and let others contribute to that analysis? What was being protected and why? Rumors began circulating. Anonymous sources, claiming to be NASA employees, posted on forums about classified briefings to congressional intelligence committees, about heated debates between scientific staff who wanted immediate public disclosure and administrators who were concerned about, as one leaked email phrased it, managing public expectations and preventing societal disruption. There were reports of Department of Defense involvement, though what the military's interest could possibly be in a comet leaving the solar system was unclear. The speculation grew wilder. Some claimed there were additional signals that hadn't been disclosed, that 3i Atlas was still transmitting, but on frequencies or in patterns that were being kept secret. Others suggested that the object had changed trajectory, that it wasn't following a natural ballistic path anymore. Most of these rumors were almost certainly false, the usual noise that surrounds any major event, but they flourished in the information vacuum created by official silence. Meanwhile, the object itself continued its journey. It had passed perihelion. It was now receding from the sun, moving outward toward the outer solar system at 130,000 miles per hour. Its brightness was fading as the distance increased and the solar heating decreased. The spectacular sublimation activity that had characterized its approach was diminishing. Water vapor production was dropping. The hydroxyl radical signature was weakening. In every observable way except one, 3i Atlas was behaving exactly as a comet should behave after perihelion. It was becoming less active, less visible, slowly fading back into the darkness from which it had emerged. Except for that one 11-minute transmission. Except for the mathematical message encoded in radio waves, except for the fact that it had pointed toward HD 93962 and said in effect, I came from there. That one exception changed everything. 3 weeks after the transmission, Dr. Claudia Reeves made a discovery that should have been impossible. She'd been running the signal data through increasingly sophisticated analysis algorithms, looking for patterns that might have been missed in the initial excitement of finding the prime numbers and mathematical constants. It was tedious work, the kind of thing that required staring at spectrograms and waveform visualizations until your eyes burned and your brain turned to static. But Reeves had built her career on finding needles in haystacks, on extracting signal from noise in datasets that other researchers had already abandoned as fully analyzed. And on November 19th at 2:30 in the morning, her algorithm flagged something in the amplitude modulation that made her sit up so fast she spilled coffee across her desk. There were images. Not transmitted as images, not in any format a human would recognize, but encoded in the amplitude variations using a mathematical grid system. When you arrange the amplitude values in a two-dimensional array based on the prime factorization of the pulse count, when you assigned brightness values to the amplitude levels, patterns emerged. Simple at first. Geometric shapes, a circle, a triangle, a square, then more complex. A representation of an atom with a nucleus and electron orbits. A double helix structure that could only be DNA or something functionally equivalent. A diagram of a star with planets orbiting it. One planet clearly marked, highlighted, designated as significant. The images were crude, low resolution, constrained by the limited data capacity of an 11-minute transmission. But they were unambiguous. Someone had carefully designed this signal to communicate visually as well as mathematically, to reach recipients who might understand pictures even if they couldn't decode the more abstract information layers. The star system diagram was particularly detailed despite its simplicity. 7 planets arranged in increasing orbital distances. the third planet marked with a symbol that repeated throughout the other images. That symbol appeared next to the DNA helix. It appeared next to what looked like a representation of a spacecraft or probe. It appeared next to a series of marks that, when counted, totaled to a number that matched the estimated age of the HD 93962 system. Everything pointed back to that third planet, HD 93962b. The signal wasn't just saying, I came from this star system, it was saying, I came from this specific world. Life exists there. Intelligent life. Life that understands biology and mathematics and space travel. Life that sent me here. But there was something else in those images that made Reeves pause, that made her triple check her decoding algorithm before she reported it to the broader research team. One of the images showed what appeared to be a timeline. A series of markers, evenly spaced, leading from a point marked with that same planetary symbol to a point marked with what could only be interpreted as our sun. Between those 2 points were hundreds of smaller markers, regularly distributed, like mile markers on a cosmic highway. When she calculated the spacing, when she tried to determine what distance each marker might represent, the numbers didn't make sense at first. They were too large, too vast, but then she realized what she was looking at. Each marker represented approximately 50 million years, and there were more than 140 of them between HD 93962 and our solar system. 7 billion years. The timeline image was confirming what the trajectory data had suggested. This object had been traveling for 7 billion years. The implications were staggering enough that Reeves hesitated before publishing. 7 billion years ago, the universe was half its current age. The Milky Way was smaller, denser, still forming new stars at a prodigious rate. Earth hadn't yet developed an oxygen atmosphere. The sun was 30% dimmer than it is today. And somewhere, around a star in what would eventually be designated the constellation Carina, as seen from a planet that hadn't yet evolved complex life, a civilization had built something, had launched something, had sent it out into the galaxy with a message encoded so carefully, so redundantly, that even after billions of years of cosmic radiation damage, even after passage through who knows what environments and conditions, the message could still be decoded, still be understood, still say, we were here, we existed, we reached for the stars, remember us. The radiation crust problem had been bothering physicists since the James Webb Space Telescope observations months earlier. Webb had detected that the outer 50 to 65 feet of 3I Atlas had been fundamentally transformed by cosmic ray bombardment. The pristine ices and organic compounds that might have existed when the object first left its home system had been cooked, irradiated, chemically altered into something else entirely. Carbon monoxide had been converted to carbon dioxide. Water ice had been restructured. Complex organic molecules had been broken down and reformed into simpler, more stable configurations. The surface wasn't a time capsule from HD 93962 anymore. It was a record of the journey itself, a palimpsest where the original text had been overwritten by billions of years of radiation exposure. So how does a heavily irradiated ball of ice and rock generate a radio signal? Dr. Franz Müller at the Max Planck Institute for Radio Astronomy had been working on this question obsessively, building increasingly complex models of possible natural mechanisms. Piezoelectric effects in crystalline structures could work in theory, but the crystals would need to be aligned, organized in ways that random accretion processes don't produce. Plasma interactions in the coma, the cloud of gas surrounding the nucleus, that could generate radio emission, but only broadband noise, not a narrow, stable carrier wave. Magnetic field oscillations? Possible, but 3I Atlas showed no evidence of an unusually strong magnetic field, and the signal polarization didn't match what you'd expect from magnetic processes. Every natural mechanism Muller modeled fell short in some crucial way. Either it couldn't produce the observed frequency stability, or it couldn't account for the narrow bandwidth, or it couldn't explain the mathematical encoding. His latest paper, submitted to the Astrophysical Journal and already circulating in preprint, concluded with unusual bluntness for an academic publication. The natural generation of the observed signal requires physical processes that are not currently understood, or the coincidental alignment of multiple low-probability phenomena. The artificial origin hypothesis remains more parsimonious. But if the origin was artificial, if there was something inside 3I Atlas capable of generating that signal, how had it survived? How do you build electronics that function after 7 billion years? Human spacecraft start degrading within decades. The Voyager probes, launched in 1977, were already operating on backup systems and failing instruments by their 50th anniversary. The idea of any technology remaining functional across billions of years seemed absurd, unless you designed for it. Unless you built redundancy into every system, unless you used materials and architectures that were resistant to radiation damage, that could self-repair, that didn't rely on delicate components prone to failure, unless you kept the systems dormant for the vast majority of the journey, powered down, inactive, waiting for the trigger condition, waiting to detect a star, waiting to approach close enough that the solar radiation could charge depleted power reserves, waiting for perihelion. The timing of the transmission kept coming back to haunt researchers looking for natural explanations. Why exactly at perihelion? Why not during the approach or during the departure? Why that specific 11-minute window when the object was at its closest point to the sun, experiencing maximum solar radiation, maximum heating, maximum stress, On its structure, Dr. Sarah Chen at Berkeley proposed what she called the threshold activation hypothesis. The object, if it was indeed an artificial probe, would have been dormant during its billions of years in interstellar space. No power generation, no active systems. Just cold, inert mechanisms waiting for the right conditions. But as it approached a star, as solar radiation began to increase, power systems could begin charging. Solar panels, if they existed beneath or within the eroded crust, could generate electricity. Thermoelectric generators could harness the temperature differential between the sun-facing and space-facing sides. At perihelion, power would be maximum. And with sufficient power for a brief window, the probe could activate, could execute its programmed mission, could transmit. 11 minutes and 34 seconds might represent the entirety of the power budget available. Enough energy, carefully hoarded from solar radiation, to power a transmitter for that duration. After which the power reserves were exhausted, the system shut down, and the object returned to dormancy. It was an elegant explanation. It fit the observed behavior, and it suggested something both fascinating and melancholy. If Chen was right, 3i Atlas had been waiting for 7 billion years for that moment, drifting through the void, inert and silent, until it finally encountered another star, our star. And when it did, it used the last of its energy, the final reserves it could muster, to send one message. To say, I was built by someone. I came from somewhere. We existed. And then it fell silent again, having completed its purpose, having delivered its message, now powerless to do anything but continue its eternal trajectory back out into the darkness. The lack of a dust tail had puzzled astronomers from the beginning. Comets produce dust. When ice sublimates, it carries dust particles with it, creating those spectacular tails that can stretch for millions of miles. But 3i Atlas had shown almost no dust emission. What tail it had was primarily gas, hydroxyl radicals, and carbon dioxide, glowing in ultraviolet light. The dust component was minimal, barely detectable. For a natural comet, this was strange. Comets from our solar system, even those with unusual compositions, produce dust. But what if 3i Atlas wasn't just ice and rock? What if the interior contained something else? Something more substantial, more structured, more resistant to sublimation? The outer layers were definitely comet-like. The spectroscopy confirmed that. Water ice, carbon dioxide, simple organic compounds, all the expected material. But beneath that, shielded by 65 feet of radiation-processed crust, there could be something entirely different, something that wouldn't produce dust when the outer layers eroded, something metallic perhaps, something manufactured. Dr. Rona Majolo, whose work on the radiation crust had been crucial to understanding the object's surface conditions, published a revised estimate that changed the calculations. The crust might not be uniformly thick. Cosmic ray penetration depth depends on the density and composition of the material. If the interior was denser than assumed, if there were pockets of different composition, the crust could be thinner in some regions. And at perihelion, with the intense solar heating, with the rapid sublimation of surface ices, erosion could have been significant, perhaps enough to expose deeper layers, perhaps even enough to expose something that had been buried beneath the crust for billions of years, something that had remained pristine, protected, waiting, and once exposed briefly, it could have functioned, could have transmitted, before being covered again, or before depleting its power, or before whatever mechanisms had survived 7 billion years finally failed. The spectrum observations from multiple telescopes showed something that hadn't been emphasized in the initial reports. Trace metallic signatures, iron absorption lines, faint but present, possible aluminum, though the detection was at the edge of instrumental uncertainty. Comets don't typically show strong metallic signatures. They're made of ice and rock and organic tars, materials from the primordial solar nebula, pristine samples of the materials that existed when the solar system formed. Metals exist in comets, but in tiny quantities, locked into mineral grains. They don't usually show up prominently in spectra. But 3i Atlas was showing metals. Not abundantly, but detectably. Enough to make spectroscopists look at each other and quietly, in conferences and email exchanges, ask the question nobody wanted to say too loudly: are we seeing interior structure? Are we seeing the probe itself? Let's consider what it means if the signal is natural. If somehow, through physical processes we don't yet understand, an irradiated comet generated a mathematically structured radio transmission at the hydrogen line frequency during its perihelion passage, we'd be discovering new physics. We'd be finding that nature, under certain extreme and unusual conditions, can create patterns that look designed, that encode information, that appear to carry intentional messages. The scientific value of that discovery would be immense. It would revolutionize plasma physics, radio astronomy, maybe even quantum mechanics if the mechanism involved some exotic form of quantum coherence in sublimating ices. Applications would follow. New ways to generate coherent electromagnetic radiation. New understanding of how matter behaves under extreme conditions. Potential breakthroughs in fields we can't even predict. But the natural hypothesis requires accepting a series of remarkable coincidences. That the signal happened to emerge at exactly the hydrogen line frequency, the one frequency most associated with searches for extraterrestrial intelligence. That it happened to encode prime numbers, the universal signifier of mathematical understanding. That it happened to encode mathematical constants to high precision. That it happened to include coordinate data pointing back to the object's origin system. That it happened to occur precisely at perihelion, at the moment of maximum observability. Each of these individually might be dismissible as coincidence, as humans finding patterns in randomness, as our species' tendency to see design where none exists. But collectively, Dr. Jill Tarter, who spent decades leading SETI research, said it plainly in an interview. We built SETI to look for exactly this kind of signal. Narrow bandwidth, hydrogen line, mathematical content. If we now argue that it's not sufficient evidence, we're essentially saying we don't know what would be sufficient. We're moving the goalposts because we don't like where the ball landed. The natural hypothesis also fails to explain intent. Random physical processes don't point to their origin. A pulsar doesn't transmit its coordinates. A magnetar doesn't encode the history of its formation. Natural phenomena happen. They don't communicate. They don't structure information for an audience. The signal from 3i Atlas wasn't just organized, it was pedagogical. It started simple, with primes, establishing that mathematics was the language. It progressed to more complex constants, demonstrating sophistication. It provided coordinates and timeline data, giving context. It included images, offering visual information for species that might process information that way. This is the structure of a message designed to be understood by unknown recipients. This is how you communicate across the vastness of space and time when you don't know who might eventually receive your transmission. You build in redundancy. You use multiple encoding schemes. You start simple and build complexity. You provide context and verification. The signal from 3i Atlas did all of this. Nature doesn't do this. Nature doesn't teach. So let's accept, at least hypothetically, that the signal was artificial. That 3i Atlas is, or contains, a probe constructed by the civilization that arose around HD 93962 approximately 7 billion years ago. What does that tell us? First and most fundamentally, we are not alone. The universe has produced intelligent, technological life at least twice. Probably many more times, but we can now say with confidence, at least twice. The question that has haunted humanity for millennia. The question that motivated every SETI program and every exoplanet survey has an answer. Yes, they exist, or they existed. Second, interstellar travel is possible. Not just theoretically possible, not just something we can imagine in science fiction, but actually achievable. A civilization reached a level of technological sophistication that allowed them to build probes capable of crossing the vast gulfs between stars. Not quickly, not in time frames that would allow for dialogue or commerce, but successfully. They could send their messages, their artifacts, their legacy across light years and have those objects arrive intact and functional. Third, such civilizations think in time frames that dwarf human history. 7 billion years. Our entire civilization, from the first cities to the present, spans 10,000 years. The Roman Empire, which feels ancient to us, collapsed 1,500 years ago. The pyramids were built 4,500 years ago, and we marvel at their longevity. But this probe was traveling for 7 billion years. For comparison, 7 billion years ago, the Earth was barely habitable. The sun was dimmer. The atmosphere was different. The most complex life was single-celled. Everything that we consider the history of complex life on Earth, everything from the Cambrian explosion to the evolution of humans to the development of technology, all of it happened during the time this probe was traveling. The civilization that built it either planned for timescales that are literally incomprehensible to human psychology, or they built probes that could outlast their own existence. Either possibility is staggering. Consider the technology required. Power systems that can remain functional across billions of years, information storage that doesn't degrade, materials that resist cosmic ray damage, micrometeorite impacts, the slow erosion of interstellar dust. Mechanisms that can detect approaching stars and execute programmed responses. Transmitters that can activate after eons of dormancy. We struggle to build spacecraft that last decades. The Voyager probes, our most durable interstellar ambassadors, are less than 50 years old and already failing. Their radioisotope power sources are depleting. Their instruments are shutting down. Within another decade or two, they'll be silent hulks, devoid of power, unable to communicate. Dead in all but name. Yet they'll continue traveling through interstellar space for billions of years, carrying their golden records, messages that will never be played because the record players will have long since ceased functioning. The engineering gap between what we can build and what 3i Atlas represents is so vast it might as well be magic, unless the probe has failed. Unless what we observed was the dying gasp of systems that have been degrading for billions of years. Maybe the transmission was supposed to be longer, more detailed, richer in content. Maybe there were supposed to be responses to any signals the probe detected. Maybe it was supposed to adjust its trajectory, to enter orbit around interesting planets, to deploy subprobes for detailed observation. Maybe the original design included all of that and more, but after 7 billion years of cosmic punishment, only the most basic systems remained functional. Only the transmitter. Only the core message. Only 11 minutes and 34 seconds of power before final, irreversible system failure. We might be witnessing not the successful operation of an ancient probe, but its death, its final moments. The last thing it could do before the cumulative damage of its impossible journey finally overwhelmed even its robust design. If the civilization that built 3i Atlas still exists, they've been technological for at least 7 billion years. Let that sink in. Human technology is roughly 200 years old, if we're being generous, dating to the Industrial Revolution. Radio technology is about 130 years old. Space travel is 70 years old. Digital computers are 80 years old. In the cosmic blink of an eye, we went from horses to spacecraft. If our technology continues developing for another 100 years, we'll have capabilities that would seem godlike to people living today. Artificial intelligence that truly thinks. Genetic engineering that can redesign biology. Nanotechnology that can manipulate matter at the molecular level. Fusion power. Quantum computers. Technologies we can't even imagine yet because we don't have the conceptual frameworks to think about them. Now multiply that rate of progress by 70 million. That's how much longer they've had if they're still around. Not 70 years. 70 million times 70 years. The gap between us and them would be so enormous that we might not even be able to recognize their technology as technology. It would look like natural phenomena to us because we'd lack the conceptual tools to understand what we were seeing. Arthur C. Clarke said any sufficiently advanced technology is indistinguishable from magic. But this goes beyond that. This would be technology indistinguishable from the fundamental fabric of reality itself. They could be manipulating space-time. They could be engineering on galactic scales. They could have transcended physical form entirely, uploading themselves into substrates we can't detect, living as patterns of information in quantum fields or higher dimensions or structures that don't have names in any human language, or they're extinct. That's the darker possibility, and in some ways the more likely one. 7 billion years is a long time. Longer than any star like our sun will live. HD 93962 is older than our sun, but not by that much. It is perhaps another 5 billion years before it exhausts its hydrogen fuel and begins expanding into a red giant. The civilization that built 3i Atlas might have thrived for millions or even billions of years, might have achieved wonders we can't imagine, might have spread across their star system or even to neighboring stars, but they're not there anymore. Maybe they destroyed themselves. War, environmental collapse, uncontrolled AI, engineered pathogens, any of the existential risks we worry about, they might have succumbed to. Maybe they evolved into something we wouldn't recognize as life. Maybe they simply faded, grew old as civilizations do, lost the spark that drove them to explore, turned inward and gradually declined into extinction. Maybe a natural disaster claimed them, an asteroid impact, a nearby supernova, a gamma ray burst. The universe is full of ways to die, and 7 billion years provides ample opportunity for catastrophe. If they're gone, the probes are their legacy, their immortality, the only evidence that they ever existed. Scattered across the galaxy, thousands or millions of these objects traveling on trajectories calculated billions of years ago, visiting stars that didn't exist when they were launched, carrying messages to civilizations that hadn't evolved yet. Some of those probes will still be traveling when our sun dies. When Earth is a cold, dead cinder orbiting a white dwarf remnant, these probes will still be out there, crossing the galaxy, delivering their message. We were here. We existed. We built things that outlasted us. We sent our thoughts to the stars. Remember us. The strategic implications were being discussed in rooms the public would never see. Defense Department analysts, intelligence community briefings, National Security Council meeting. The questions being asked weren't scientific. They were tactical. If interstellar probes exist, how many are there? Are there others in our solar system that we haven't detected? Could they pose a threat? The answer to the last question was almost certainly no, at least not in any conventional sense. 3i Atlas had shown no capability for violence, no weapons, no threatening behavior. It transmitted a message and continued on its way. It couldn't maneuver. It couldn't change course. Even if it wanted to impact Earth, its trajectory made that impossible. It had passed perihelion. There was no scenario where it posed a physical danger. But information could be dangerous. What if the signal contained more than we'd decoded? What if there were instructions embedded in it? Coordinates to other probes, technical specifications for weapons we haven't conceived of, nanotechnology blueprints, artificial intelligence seed code. The signal had been broadcast publicly, received by multiple facilities, analyzed by researchers worldwide. If there was something dangerous in it, it was already out there, already in human hands, already being studied in laboratories and universities across the planet. You couldn't contain it now, even if you wanted to. The only question was whether there were additional layers still hidden in the data, still waiting to be discovered, that might change the equation. Some analysts argued the probe itself was a security concern, not as a weapon, but as a prize. If it contained technology 7 billion years advanced beyond ours, even degraded, even barely functional, the technological insights could be revolutionary. Whoever understood how it worked, whoever could reverse engineer even a fraction of its systems, would have an overwhelming advantage. The object was leaving the solar system. Soon it would be beyond reach, but theoretically, not impossibly, a mission could be launched. A fast probe. Nuclear propulsion, maybe. Ion drive. Launch in the next year or two, catch up to 3i Atlas in a decade or so while it's still within the outer solar system or just beyond. Rendezvous with it. Study it up close. Maybe even capture it. Bring it back or at least transmit detailed analysis. The technological payoff could be enormous. Power generation. Material science. information storage, computing. Any of those could be transformed by understanding how this probe worked. The problem was that such a mission couldn't be secret. Launching a spacecraft requires enormous infrastructure. Rockets are visible. Trajectories are trackable. If one nation launched a mission to intercept 3I Atlas, others would know immediately. Would they accept it? Would there be international cooperation, a shared scientific mission for the benefit of all humanity? Or would there be competition, multiple nations racing to be first, to claim the prize for themselves? Could it trigger conflict? The optimists said no, that the scientific community would demand cooperation, that the United Nations would broker an agreement, that humanity would rise to the occasion and treat this as a shared heritage moment. The pessimists remembered every previous example of nations competing for strategic advantage and expected exactly that pattern to repeat. The realists noted that the mission was probably impossible anyway with current technology and budget constraints, so the whole debate was premature. But the conversations were happening. The plans were being sketched. The feasibility studies were being commissioned. November 28, 2025, 29 days after the transmission, 3I Atlas is now 0.68 astronomical units from the Sun, roughly the distance of Venus's orbit, and receding at a steady 130,000 miles per hour. Its brightness has faded to magnitude 14, too dim for amateur telescopes, requiring professional equipment and long exposures to observe. The spectacular sublimation activity that characterized its approach has diminished substantially. Water vapor production has dropped to less than 10% of its perihelion peak. The hydroxyl signature, that telltale marker of water molecules breaking apart in sunlight, is weakening daily. The object is behaving exactly as comet physics predicts: cooling, quieting, fading back into dormancy as it retreats from the sun's warmth. Except everyone watching knows what it did. Everyone remembers those 11 minutes and 34 seconds, and that knowledge transforms every subsequent observation from routine data collection into something that feels like vigil, like watching someone you know carries a secret, waiting to see if they'll speak again. They haven't. The radio silence since October 29th has been absolute. The Allen Telescope Array maintains continuous monitoring whenever 3I Atlas is above the horizon. Green Bank dedicates observation time every day. China's Fast Telescope, the largest single-dish radio telescope on Earth, points at the object during its available windows. The Very Large Array in New Mexico conducts sweeps across multiple frequencies, not just the hydrogen line, looking for any emission that might have been missed. Amateur radio astronomers around the world have formed coordination networks, providing near-continuous coverage as the object moves across the sky. Thousands of hours of observation time, petabytes of data, all of it analyzed, scrutinized, processed through every signal detection algorithm available. Nothing. Just the cosmic background hiss, the static of space itself. Whatever energy 3I Atlas had to communicate, it expended completely during that first and only transmission. Dr. Sofia Ramirez, who first detected the signal, hasn't stopped analyzing the original data. She's running it through new algorithms weekly, looking for patterns that might have been missed, structures that require more sophisticated decoding, and she keeps finding things, small things, subtle variations in the signal that might be noise or might be additional encoding layers, so compressed, so efficiently packed, that they require computational approaches that didn't exist when the signal was first analyzed. Machine learning models trained on the data are identifying correlations that human researchers can't see directly, patterns in the micro-timing of pulses, variations in polarization that occur at scales of milliseconds. It's possible, increasingly likely even, that the 11-minute transmission contains far more information than anyone initially estimated. The prime numbers and mathematical constants and coordinate data might be just the outermost layer. The introduction, the hello, we're intelligent greeting. Beneath that could be compressed data, information packed with an efficiency that human information theory hasn't achieved yet. Gigabytes or even terabytes of data hidden in what appears to be a simple signal, waiting for sufficiently advanced analysis to extract it. The decoding efforts have become international projects. The 3I Atlas Signal Consortium now includes researchers from 63 countries, operating under a data-sharing framework that makes all findings immediately public. No nation has proprietary claim to the analysis. No institution holds exclusive access. The raw signal data is available for download to anyone with an internet connection. High school students are running decoding attempts as science fair projects. Citizen scientists are contributing processing power through distributed computing networks. Universities are offering courses on interstellar signal analysis using the 3I Atlas data as the primary case study. In a strange way, the signal has become humanity's shared project, something that transcends borders and politics, a mystery that belongs to everyone equally. Whether that cooperation will survive if something truly revolutionary is decoded remains to be seen. HD 93962 has become the observed star in the sky outside our own solar system. James Webb Space Telescope time, normally allocated through a competitive process months in advance, was cleared in an unprecedented emergency reallocation. 100 hours of observation time focused on HD 93962b, the super-Earth planet orbiting in the habitable zone. The goals are specific: detect atmospheric composition through transit spectroscopy, Look for biosignatures like oxygen and methane in combinations that suggest biological activity. Search for technosignatures like industrial pollutants or artificial light emission on the night side. The observations began on November 15th and will continue through January 2026. Results are being analyzed in real time, with preliminary findings released weekly. So far, the planet definitely has an atmosphere. Nitrogen is present, oxygen is present, carbon dioxide is present. The ratios are unusual, not quite like Earth, but not incompatible with life. More detailed analysis is ongoing, but there's something else they found that hasn't been publicly announced yet. Something that's being carefully verified before anyone is willing to put it in a press release. The night side of HD 93962b, when it passed in front of the star during transit, showed faint emission or infrared. Very right at the edge of detection. It could be instrument noise, it could be atmospheric phenomena, aurorae perhaps, natural light emission from the planet's upper atmosphere, or it could be artificial light. Cities on the night side of a planet emit light. Not much compared to the brightness of the star, but detectable if you're looking carefully enough and you have an instrument as sensitive as the James Webb Space Telescope. The analysis teams are being cautious because the implications are extraordinary. If those emissions are confirmed as artificial, if they persist across multiple observations, if they show patterns consistent with distributed light sources rather than natural phenomena, then we're not just looking at a planet that once hosted intelligent life billions of years ago. We're looking at a planet that hosts intelligent life now, that has cities, that uses energy, that, in at least some ways, might be visible to us across 178 light years of space. The response debate has fractured humanity more effectively than almost any previous question. Should we answer? Should we transmit a reply signal toward HD 93962, acknowledging that we received the message from 3i Atlas, confirming that intelligent life exists here too? The arguments have become heated, philosophical, almost theological in their intensity. Dr. Douglas Vakoch, who has spent decades advocating for active SETI, for humanity transmitting rather than just listening, sees this as the opportunity he's been arguing. They sent a message. They're waiting for responses. That's the whole point of sending probes across the galaxy. You want to know if anyone else is out there. We received their message. Basic courtesy, basic communication ethics demands that we acknowledge receipt. We should respond, but the opposition is equally passionate. Dr. Dan Wertheimer at Berkeley SETI argues that we don't know what we're dealing with, don't understand the full context, can't predict consequences. We're infants playing with technology we barely understand, and we want to announce our presence to a civilization that's potentially billions of years older than us? Stephen Hawking warned about this. He said that announcing ourselves to advanced civilizations could be like Native Americans sending up smoke signals when European ships appeared on the horizon. It didn't end well for the Native Americans. Maybe, just maybe, there are reasons to be quiet, to listen more, to learn more before we start broadcasting. The practical problems are immense, even if consensus could be achieved. Who decides what to send? The United Nations formed an ad hoc committee, but it's been deadlocked for weeks. Every proposed message gets objections. Too technical. Not technical enough. Too focused on humanity. Not representative of Earth's diversity. Religious content is controversial. Excluding religious content is controversial. Some nations want to emphasize peace and cooperation. Others want to demonstrate strength and capability. Some groups want to send art and music. Others want to send scientific data. There's no agreement, there might never be agreement, humanity has no unified voice to speak with because humanity isn't unified, and then there's the time problem. Any message transmitted now would take 178 years to reach HD 93962. A reply would take another 178 years to return. 356 years round trip. Everyone involved in the decision to respond will be dead before any reply arrives. Their children will be dead. Their grandchildren will be dead. The response, if it comes, will arrive in the late 24th century to a civilization that might be unrecognizably different from ours, facing challenges we can't predict, possibly not even interested anymore in the question that seems so urgent today. The vast gulfs of space impose limits that no technology can overcome. The speed of light is not just fast, it's the ultimate speed limit, and it makes conversation across interstellar distances effectively impossible. You can send messages, but you can't have dialogue. You can't negotiate. You can't clarify misunderstandings. Every transmission is a statement thrown into the void with no expectation of immediate response. Some researchers suspect responses have already been sent secretly by nations or institutions that didn't want to wait for global consensus. There are unconfirmed reports of powerful radio transmissions from China's FAST telescope on November 12th, aimed at the coordinates of HD 93962, lasting approximately 15 minutes. China denies it, but denial is expected whether it happened or not. There are rumors of U.S. military transmissions, messages sent from classified facilities using equipment not publicly acknowledged. Again denied, again expected. If someone is going to unilaterally respond on behalf of humanity, they're not going to announce it. They're going to do it quietly and either claim credit centuries from now when it no longer matters, or never admit it at all. The tragedy is that we may never know what was sent, if anything was sent, what message some subset of humanity decided to broadcast to the stars without consulting the rest. The engineering discussions about intercepting 3I Atlas have progressed from speculation to actual preliminary design studies. NASA's Jet Propulsion Laboratory quietly conducted a feasibility assessment. The conclusion, barely possible with near-future technology, but extraordinarily expensive and risky. A spacecraft using nuclear electric propulsion, accelerating continuously for years, could potentially catch up to 3I Atlas sometime in the early 2040s, approximately 15 years after launch. The velocity requirements are extreme. The probe would need to accelerate to over 150,000 miles per hour and maintain that speed, something no human spacecraft has ever done. The cost estimates range from $8 to $15 billion, depending on payload and mission architecture. For comparison, the James Webb Space Telescope cost $10 billion and took decades to build. This would be similar in cost, but on a far more compressed timeline if we wanted to catch the object before it's too far away to make the mission practical. China has expressed interest. The Chinese National Space Administration released a statement noting that interstellar object research represents a priority area for deep space exploration, and that they are evaluating mission concepts for close-range study of objects of interest. It's the kind of carefully worded statement that could mean anything or nothing, but analysts read it as a declaration of intent. If NASA doesn't pursue a mission, China might. And if China launches, would the United States accept that? Would Europe? Would there be a race, multiple missions competing to be first? The international space treaties are unclear about who has rights to study or potentially retrieve an object that doesn't belong to any nation, that comes from interstellar space, that might contain technology from another civilization. There's no legal framework for this, no precedent, no established norms, just competing interests and the knowledge that whoever gets there first might gain access to something invaluable. But the harsh reality that most engineers acknowledge privately is that we probably can't reach it. Not with current budgets, not with current political will, not with the competing priorities and budget constraints that characterize modern space programs. The mission would need to be approved, funded, designed, built, and launched within the next 3 to 5 years to have any reasonable chance of intercept. That timeline is nearly impossible for a mission of this complexity. By the time the mission was ready, 3I Atlas would be so far away that the intercept velocity requirements would be insurmountable. The object is escaping. Within a few years it will cross the heliopause, the boundary where the solar wind gives way to interstellar space, and then it will be gone, back into the darkness, another wanderer among the hundreds of billions of objects drifting through the galaxy. We had our moment. We received its message. And now we're watching it leave, knowing we'll never see it again, never get another chance to study it up close, never know for certain what it truly was. The philosophical shift happening across human civilization is subtle but profound. Before October 29th, the question of whether we were alone in the universe was abstract, theoretical. People had opinions, scientists had hypotheses, but nobody knew. The Fermi paradox haunted us. If intelligent life is common, where is everybody? Why the great silence? Now we know at least part of the answer. They're out there. They build things. They send messages. They explore. We have proof, not in the form of radio signals from distant stars or the mathematical analysis of what might be possible, but in the form of an actual object, a physical thing that traveled here from somewhere else, that transmitted information we could receive and decode. The abstract became concrete. The theoretical became real. And that changes something fundamental about how we see ourselves. We're not the first. We're not the pioneers. We're not boldly going where no one has gone before. We're following paths that were laid down billions of years ago by civilizations that reached for the stars when our planet was still molten rock cooling in space. We're the newcomers, the young species, the late arrivals to a galaxy that has been inhabited, explored, and mapped by others long before we evolved. There's humility in that realization, a necessary correction to the unconscious assumption that humanity might be special, might be the first intelligence the universe produced, might be destined to inherit the stars. We're not inheriting anything. We're discovering that the inheritance was already claimed, the territory already explored, the messages already sent. We're just now learning to read them. But there's hope in it too, because if they could survive long enough to send probes across the galaxy, maybe we can too. If they could develop technology sophisticated enough to function across billions of years, maybe we can develop the same. If they could overcome whatever challenges their civilization faced to become spacefaring, maybe we can overcome ours. The great filter, that theoretical barrier that prevents civilizations from becoming interstellar, that might explain why the galaxy isn't teeming with obvious signs of life, might be behind us rather than ahead. We might be one of the ones who makes it. The existence of 3I Atlas, whatever it truly is, proves that technological civilizations can achieve remarkable things, can leave marks on the universe that persist across timescales that dwarf geological epochs. That's not just interesting, that's inspiring. That's the kind of knowledge that can change how a civilization thinks about its own future. December moves forward. The object grows dimmer, harder to observe, more distant with each passing day. The telescopes keep watching. The analysts keep searching for new patterns in the signal data. The debates continue about response, about interception missions, about what it all means. But 3i Atlas itself is indifferent to all of it. It follows its trajectory, governed by physics and momentum, carrying its secrets back into the void. It delivered its message. Whether we fully understand that message, whether we respond to it, whether we learn what we need to learn from it, that's our responsibility now. The visitor has done its part. On December 15th, 3i Atlas will cross the orbit of Mars. By February 2026, it will pass the asteroid belt. By June, it will be beyond Jupiter. Within 2 years, beyond Neptune. By 2027, it will reach the heliopause and transition back into interstellar space, beyond the reach of the solar wind, subject once again to the full fury of cosmic radiation, dormant and silent for the next billions of years until perhaps it encounters another star, another system, another chance to transmit. If it has any power left, if its systems haven't finally, completely failed, if there's anything left inside that radiation-scarred shell that can still function. We had our moment. 11 minutes and 34 seconds of contact with something that came from impossibly far away and impossibly long ago. That's what we're left with. A message in a bottle, cast onto cosmic shores by a civilization we'll never meet, carrying information we're still learning to decode. And the question that matters now, the question that will define how we move forward, is simple. What do we do with it? How does humanity change, knowing what we now know? That the universe is not empty, that intelligence exists, or existed beyond our small world. That someone out there, 7 billion years ago, looked at the stars and made the same decision we're making now. To reach out, to explore, to send our thoughts and our legacy into the darkness, hoping that someday, somewhere, someone would find them and know that we were here. 3i Atlas is still out there, receding into the black at over 100,000 miles per hour. And we're still here watching it go, knowing we heard something remarkable, knowing we might never fully understand it, knowing that the universe just became infinitely larger and more mysterious and more full of possibility than it was before. The interstellar visitor brought us a gift, not technology or power or answers to our questions, but something more valuable, proof that we're not alone. Proof that it's possible to survive and build and send messages that outlast civilizations. Proof that the cosmos is listening, has always been listening, and that somewhere in the darkness between the stars, our messages are traveling too. Carrying word that Earth exists, that we exist, that we've looked up at the night sky and wondered who else is looking back. Now we know. Someone was, someone is, and that changes everything.